distance between stacking bases. Loss of base sticking in case of ADN. So that is the major reason. The distance between two double stranded DNA stacking bases become short. Describe one factor that can make B-form DNA of given sequence have a higher melting temperature. So bDNA can be converted into aDNA when we have high salt solution due to dehydration. Binding of a molecule into the minor groove of DNA can also cause high melting temperature. And during positive supercoiling, we have high melting temperature. So high melting temperature, we have three causes for that. High salt solution, binding of a molecule in the minor groove of DNA, and positive supercoiling. Sketch a proline residue and list one of the three ways given that is a special. No backbone amino group. So in amino acid we have three groups in common. One is carboxyl group, other is mono, and third is hydrogen group. So carboxyl group, hydrogen group, and mono group is common to every amino acid except proline. Why? This amino group attach with the methyl group of this propyl. So this amino group is converted into amino group. This amino acid is converted into amino acid. That's why you can say there is no backbone amino group in the proline. There is no backbone amino group. Why? Because this amino group has attachment with this methyl group. So that's why amino group is converted into amino group. That's why proline is not an amino acid. It is an amino acid. Proline is not an amino acid. It is an amino acid. And this amino acid used to produce a kink in protein. What is kink? Kink means it is turn, slightly turn of around 35 to 45 degrees. So during alpha helical structure, proline can cause slight bend due to lack of hydrogen bonding. So you can say more stable in cis configuration. Why? Because amino group attach with the methyl group, and due to less hydrogen atom, it prefer in cis configuration because it is an amino acid, not amino acid. So it prefer in cis configuration because of only one hydrogen atom which is involved in bonding. When proline is found in alpha helix, the helix will have a slight bend due to the lack of hydrogen bond. It has less hydrogen atom as compared to other amino acid, which can make transpeptide bond. All protein are made up of amino acid, and that amino acid are linked by peptide bond. And that peptide bond has trans configuration, rigid configuration, mean like this. This is trans configuration. This carbonyl group is in the upward direction and this hydrogen is in the downward direction. And this is not possible in the proline structure. Why? Because prolines have only one hydrogen atom on its nitrogen ion. So you can say this peptide bond is transpeptide bond, and it is very rigid and it has resonating structure. Why? Because the double bond has resonating value between CO and CN. it resonate between CO and CN, CO and CN. Due to this resonating structure, it has more stability as compared to other bonds. Due to this resonating double bond between CO and CN, it has more stability as compared to other bonds. So you can write C double bond O and C double bond N. If you have a double bond here, you cannot write double bond here. If you have a double bond here, you cannot write a double bond here. So it either have double bond between CO or CN, not in both, because of resonating structure of that peptide bond. Dry transpeptide bond in two resonating forms. Include in your drawing all atoms that are in peptide blend. Here you can write one here a C double bond O and one single bond N. Then you have a C single bond O and C double bond N. Why? Because it is resonating double bond between CO, CN, CO, CN, CO, CN. That's why this peptide bond has stability because of this trans structure, and due to its resonating double bond, it has more stability and it is rigid. It cannot change its shape. It cannot change in shape due to the presence of that resonating double bond between CO and CN, which is a peptide. Here are some amino acids which have three-letter code and they are hydrophilic. All polar amino acids, acidic and basic amino acids are hydrophilic. All basic and acidic amino acids are hydrophilic. Why? Because acidic amino acid has an extra carboxylic group on their side chain, and basic amino acid contain extra amino group on their side chain. So extra carboxylic group give negative charge to amino acid, and extra amino group give positive charge to amino acid. That's why if in a protein we have more basic amino acid, it has positive charge. And if we have in a protein more acidic amino acid, what happen? It has negative charge. So basic protein has more basic amino acid. That's why they have a positive charge, like histone protein. Histone protein contain basic amino acid arginine and histidine. That's why they are positive. And the protein which have more acidic amino acid, they are negative. So serine, this is the structure of serine, which have a CH2OH group on their side chain. All amino acids have same this structure: carboxylic group, amino group, hydrogen group. These three groups are common in all amino acids. Only side chain is changed. For example, in aspartic acid, which is represented as a D, it has CH2 and carboxylic group. And in glutamic acid, we have two methyl groups, CH2, and when we have then we have carboxylic group. So in acidic amino acid, we have extra carboxylic group on side chain, and in basic amino acid, we have extra amino group on their side chain. So serine contain hydroxyl group. That serine is very important. Why? Because it help in hydrogen bonding. And it also help in it help in enzyme regulation during phosphorylation and dephosphorylation. This serine and threonine amino acid has hydroxyl group on their side chain. So both amino acids, serine and threonine, help in enzyme regulation by phosphorylation and dephosphorylation. Enzymes phosphorylation and dephosphorylation only happen in serine and threonine amino acid. which has hydroxyl group on their side. So aspartic acid has negative charge, asparagine polar but uncharged. It is represented with N sign. Arginine basic amino acid, it is represented by single letter code R. Lysine has positive charge. It is represented by K, and histidine is represented with H. And all the three is basic amino acid, arginine, lysine, histidine, have positive charge, as positive charge. So arginine, lysine, histidine are hydrophilic. Similarly, aspartic acid, glutamic acid are hydrophilic along with asparagine. For all the following pentapeptide, give the charge associated with each position at pH 7. Alanine, serine, aspartate, cysteine, histidine. So at physiological pH, most of the neutral amino acid contain zwitterionic form. Mean their amino group has extra positive ion, and carboxylic group do not have a proton. So during a protein formation, we have two terminal. One is C terminal, which end at carboxylic end, and other is N terminal, which start with the amino group. So all protein have two ends. One is N terminal, which is starting point, and other is C terminal, which is end point. Start point always amino group, end point ends with carboxylic group. So in at physiological pH, last carboxylic group has negative charge and first amino group has a positive charge, just like amino acid, just like amino acid. Amino acid at their neutral pH have zwitterionic form, mean it has positive charge on amino group and negative charge on carboxylic group. So we have charge on last amino acid and last first amino acid. First amino acid has a positive charge, and last amino acid has a negative charge. But this we have another amino acid which is polar, aspartic acid. Aspartic acid pK value 3 is 4, and it has -1 charge, because this pH is less than 7. So we have extra carboxylic group which has negative charge at pH 7. So net charge on that protein is +1, -1 cancel each other, then -1, negative charge. So this pentapeptide has net negative charge on it. What we can do to remove that negative charge? We add some acid which can protonated that carboxylic group which are present in the side chain of aspartic acid. So what is the pi, isoelectric point of that pentapeptide? The isoelectric point is around 5. Why? To remove that negative charge, we add an acid. And what is isoelectric point of that protein? The protein which do not have any charge at specific pH, this is known as isoelectric point of that protein. So if we add acid into that protein, then the isoelectric point is around 5. Why? At pH 5, this carboxylic group is also protonated, and we have a net charge on protein is 0. So take two pK value. One pK value of aspartic acid, and other is the pK value of histidine. pK value of side chain of aspartic acid is 4, and other basic amino acid is histidine, which is pK value is around 6. Take the average of these two amino acid, and we have a pi. pKa of aspartic acid is 4, and histidine is around 6. So 4 plus 6 is equal to 10, divided by 2 is equal to 5. So net charge on protein becomes 0 if we have pH of 5. That's all. If you have any question, you can ask, please.
That's it. Yeah. Thank you. Yeah, that makes sense.
We can stop recording over here.
Oh, yeah.
I will share that recording.